Welcome to The Explainer, where we tackle big, complex topics and break them down into clear, visual stories. Okay, get this. Can a greenhouse gas actually help us produce more fossil fuels? I know, it sounds totally backwards, right? A complete contradiction. But believe it or not, that is the core idea behind a technology sitting smack in the middle of the whole climate debate. And that technology is called carbon capture, utilization, and storage, or CCUS for short. Today, we're going to dive into how this all works, what it promises to do for our energy future, and exactly why it has become so incredibly controversial. To really get a handle on the controversy, we have to start with what captured carbon is actually used for most of the time. And spoiler alert, it's about getting more oil out of the ground. So just picture an oil field for a second. After companies have pumped out all the easy-to-get oil, there's still a ton of it left down there. Sometimes as much as 40% is still stuck in the rock. It's not hiding, it's just really, really hard to get out with the usual methods. So you could imagine, for an oil company, that's the billion-dollar question. How on earth do you get that valuable, trapped oil to finally start flowing again? Well, the whole problem really comes down to one word: viscosity. That leftover crude oil is super thick and sticky. Think about trying to drink honey through a straw versus water. The goal here is to somehow make that thick, sludgy oil a lot thinner so it can actually move. And this is where CO2 makes its grand entrance. The process is called enhanced oil recovery, or EOR. First, engineers pump captured CO2 deep underground right into that oil reservoir. The CO2 then works its magic. It dissolves into the oil, making it swell up, and, this is the key part, it makes it way less viscous. Now, this thinner, more mobile oil can be pushed toward a production well and pumped to the surface. And the CO2 that comes up with it, they just separate it and pump it right back down to use it again. And this image really drives the point home. You see, the oil isn't just sitting in a big underground lake. That would be too easy. No, it's locked inside the tiny microscopic pores of the rock itself, kind of like water in a sponge. The CO2's job is to get in there and basically wash that oil out. So when you hear people talk about this, especially its supporters, it's often framed as the perfect win-win. You know, a win for the economy and a win for the environment. What could be better? And the economic argument, well, it's pretty powerful. The idea is that EOR creates a huge, valuable market for captured CO2. This gives companies a financial reason to capture their emissions in the first place, because that CO2 is now a product they can sell. And that revenue helps pay for the incredibly expensive carbon capture systems. But to make this market a reality, you need some serious infrastructure. We're talking about a massive network of pipelines to move all this compressed CO2 from a power plant to an oil field. And this isn't just some drawing on a whiteboard. There are already thousands of miles of these pipelines operating in North America right now. Okay, this brings up a pretty obvious question, right? If you're pumping a greenhouse gas deep underground, what's to stop it from just leaking back out into the atmosphere? The industry's answer to that is actually pretty simple: money. The CO2 isn't just waste, it's a valuable asset that companies pay good money for. So if it leaks, they're literally losing money. That creates a really powerful financial incentive to keep it contained so they can use it over and over again. So that's the theory, that's the promise. But now let's zoom out and look at the real-world track record of these projects, because that's where things get, well, a lot more complicated. First things first, where is all this captured carbon actually going today? This chart tells a pretty stark story. A whopping 80% of it is not being put into some dedicated underground vault just for climate storage. Nope, it's being used for enhanced oil recovery. In other words, to produce more fossil fuels. And then there's the success rate, which isn't exactly a glowing report card. After decades of talk and investment, the story of large-scale CCUS is mostly a story of projects that never happened. About 70% of the projects that get announced are either canceled or just failed to get off the ground. But wait, it gets even more dramatic. If you look specifically at the power industry, at coal and gas plants, the failure rate is just staggering, over 98%. For technology so often pitched as a key solution for clean power, that track record is incredibly poor. So why is the failure rate so high? A huge part of the answer is something called the energy penalty. Here's the catch-22. The process of capturing carbon takes a lot of energy. That means a power plant with carbon capture has to burn way more fossil fuel, up to 40% more, just to generate the exact same amount of electricity. It's like taking 2 steps forward and 1 big step back. So you take all of this, the promise, the costs, the failures, and you can see why this has sparked such a fierce debate. Is CCUS a genuine climate solution, or is it just a form of greenwashing? And that debate really has 2 clear sides. On one hand, supporters say, look, this is a pragmatic, necessary tool, especially for heavy industries like cement and steel that are super hard to clean up. But on the other side, critics argue that it's a wildly expensive distraction that just provides a lifeline for the fossil fuel industry to keep on going. Which brings us to what might be the single most important question in this entire discussion. When you add everything up, what's the net effect? Does using captured CO₂ to get more oil out of the ground actually reduce overall emissions? And the answer is it completely depends on who you ask and what assumptions they make. The research is totally split. Some studies conclude that when you burn that extra oil, the whole process actually increases total emissions. But other studies find there's a net benefit. But, and this is a huge but, that only works if you assume this new oil replaces other, dirtier oil, instead of just being added to the world's total supply. And that's a very controversial assumption. So let's try to put a bow on this. Where does all of this leave us? You know, after decades of investment and debate, the bottom line is that CCUS is still a technology with a tiny, tiny footprint. It captures less than 0.1% of global emissions each year. It is clearly not a silver bullet. Now, that's not to say it's useless. Many argue it could play a vital role for tough industries like cement. But for now, its high costs, spotty track record, and deep connection to oil production guarantee it will stay at the very center of the climate debate. And this leaves us with the final, big question. Is this technology a necessary bridge to help us transition to a green future, or is it just an expensive detour that keeps us tied to the energy systems of the past? Ultimately, the answer won't just come from engineers. It will be defined by the economic and political choices we all make next.